Greetings, math fans. All right, so this is day 3, and we're talking about actually 3 different things today. But before we get started with the handouts, which you guys should have in your hand, hopefully, I want to talk about one-sided limits. All right, and we're going to use one-sided limits to determine if the function has a derivative at a specific point. Okay, so I want you guys to remember that if the limit as x approaches some value from the positive side is equal to the limit as x approaches some value from the negative side. So basically, we're saying if that two-sided limit exists, right, and obviously it's got to also equal f of x, because what is this? This also shows that it's continuous at that point, right? It exists at that point. Then it has a derivative. Okay, so let me give you an example here. If I give you y is equal to 2x over, a nice little piecewise function here, 2x squared minus 3 and 4x plus 2. So it's 2x minus 3 when x is less than or equal to 1, and this is where x is greater than 1. All right, what I'm going to do is I'm going to check out the left-hand side and the right-hand limit. I'm going to see if they're equal. So we're going to do limit as h approaches 0 from the negative side. Okay, and of course we're just going to, I'm going to put kind of our old definition of finding the slope of a tangent line, right? I'm not going to find the function, I'm just going to find the slope, because I don't need to find the function. I'm just literally looking for the slope at x equals 1. So we're going to get 2, and then it's going to be 1 plus h, right? A plus h minus 3 minus, and then in brackets, 2 times 1 squared minus 3 all over h. Okay, and we simplify that. It's going to be, this is squared here. 2, and this is 1 plus 2h plus h squared minus 3, and that's going to be 2 times 1 is 2 minus 3 is negative 1, so it's really minus, I'll just show a little work here, all over h. So limit as h approaches 0 from the negative side, that's going to be 2 plus 4h plus 2h squared. That's going to be plus there, so it's going to be minus 2 all over h. So we have limit as h approaches 0 from the negative side. The 2's cancel, and we get 4h plus 2h squared all over h. And then I can rewrite this by factoring out at h. 4 plus 2h over h. That cancels. And then I can do direct substitution. So that's going to be 4 plus 2 times 0, which is equal to 4. Okay, so that's the slope of the line coming from the left-hand side. Okay, so let's look at the slope coming from the right-hand side. Limit as h approaches 0 from the positive side of 4 times, again we're putting a 1 here, so 1 plus h plus 2 minus, and in brackets, 4 times 1 plus 2 all over h. So limit as h approaches 0 from the positive side, that's going to be 4 plus 4h plus 2 minus, and that's 4 plus 2 is 6. So it's going to be minus 6 all over h. Limit as h approaches 0. Okay, so that's 4 plus 2 is 6, minus 6 is 0. So really you have 4h over h, and that just reduces to 4. Alright, sweet, look at that, man. The one-sided limits are the same. That means my slopes of these lines are the same. Slope of the tangent lines at that point are the same. So does that make it differentiable? Well, what did I say at the beginning, right? In order to be differentiable, the two-sided limits has to exist. So the one-sided limit has to be equal to each other, but also it has to be equal to f of x. So I need to check for continuity. Okay, math fans, this is really what you should have checked first. I just want to show you the one-sided limits as an example, but truly you need to check for continuity. And if I plug a 1 into there, I get 2 times 1 squared minus 3. That's equal to -1. And 4 times 1 plus 2 is equal to 6. Boo! Not continuous. So it's discontinuous. So that means it is not differentiable. Oops, there's probably a Yox right here that says not differentiable. Okay, but it is discontinuous because of the -1 and 6. Very important. Okay, let's go on to one of our handouts here now. I want to talk about the Bear Creek handout, and so these are basically elevations along Bear Creek. Don't really know where Bear Creek is, but I'm sure if you do Google on it, you could find it someplace. And basically with the elevations, you have the distance downriver. So how far? In other words, we're at the top of the mountain at 0, and then you keep moving down the river, 0.56 down the river, 0.92, etc. And then it tells you your elevation as you go down. Okay, so I actually created the slopes between the points, which is really what the derivative is, isn't it? It's a slope between those, and we kind of learned that the average rate of change back in the day, right? So I can find the slopes between 1577, 1512. It's y over x. So 1512 minus 1577 over 0.56 minus 0.00, and so that gives us our slope at that, or between those points, right? Our derivative, our slope of that tangent line at that point. And you can see with the slopes, so you have negative point or negative 116.07, negative 178, etc. And so let's look at a couple questions here that they ask, given all that information. It says, note the midpoint method is used to create the derivative column, and we learned that back in the day. It's midpoint. It's given data. You want to basically use one or two pieces of data to find that slope. That gives us, again, it's an estimate of the derivative. Okay, so what is the unit of the measure for the derivative? Well, I mean, you can kind of look at this. It's pretty easy. It's the 1577 and 1512 are used, so it's going to be feet on top and miles on the bottom, right? So our unit of measure is feet per mile. Okay, and again, well, I shouldn't say again, but this is called the gradient. All right, and the way this kind of works, math fans, if you've been down a river, as the river drops, or I should say as the river progresses, so it's 0 miles and 0.56 miles and 0.92, the elevation drops, because that's kind of how a river works. The drops in elevation, and that's what causes the river to actually flow, right? It doesn't flow up a mountain. So it flows down, down, down. And the deal is, where does the river flow the fastest? Well, it doesn't flow the fastest where it drops the most, okay, or has the steepest slope, okay? Very interesting, the steepest slope. So if I look for the steepest slope here, you will see that it's between these values right here. So that's my steepest slope. Okay, so the answer to that question is between well, you can even see these values down here, right? Let me highlight this guy right here. So it's between 1.3 and 1.39 miles downriver. Okay, so between 1.3 and 1.39. That's the most dangerous part because it's the steepest slope or steepest part of the mountain, right, where it's dropping the fastest. All right, and then I have a last question here. It says estimate the rate of change at 2.08 miles. Well, I go to 2.08 and it's somewhere between 2 2.18 and 1.98. Okay, so it's going to be somewhere between those two values. Do you guys agree with that? So if I want to find the estimate that rate of change, I'm going to use this value right here. Again, it's between 2.18 and 1.98, which is this guy right here. And that's my average. My average is negative 320. Okay, so that is just that's estimating the range or the rate of change at 2.8 miles. So I'm just going to say negative 320 feet per mile. Okay, pretty straightforward. All right, so that's kind of it. I just want to show you really using data. What you use to find the derivative or to find that slope is you're using really the midpoint formula for all these problems. Okay, let's do a little more practice now. I created an F graph, and I wanted to draw the F prime graph just to kind of get a little more practice. Well, whenever you see a straight line in an F graph, you know it's a constant slope. Okay, and so and remember, x units are x units on a slope graph or a F graph, and the y units are slope units on an F prime graph. Okay, so notice I don't really even have I don't have tick marks, and I don't necessarily know tick marks for the curved parts, but I do know tick marks, so I'm going to put these on here. I know them for the straight values. So if I look between 0 and 1, do you agree I go up 3 over 1? So my slope is 3. From 0 to 1, it's 3. So from 0 to 1, it's 3, right? Here, let me just label it 1, 2, 3. Negative 1, negative 2, negative 3. Okay, and then I go from 1 to 4, and you guys agree it goes 1 down 2 over 1, 2, 3. So it's negative. So this is like a negative 2/3 slope here. This was a 3 slope. So that means I go down to negative 2/3, and I have an open dot, and I go from 1 to 4. All right, so again, that's a constant slope. And then from 4 to 6, what's my slope? My slope is 0. So I go at 0 from 4 to 6. All right, so that's my slope graph so far. Now that's actually pretty easy because again, they're constant slopes. Now let's look at from 6 to 8. Okay, so it starts out at 0, right? 0 slope, and then it starts to increase. And do you guys agree? Let's look at a couple points here. Do you agree that this point on top here, that slope is 0, right? Okay, it's a maximum or minimum point, but the slope is 0 at 8. So I'm going to go to 8 right here, and I'm just going to plot a point here because I know it's equal to 0. And then I want to say, well, where's the steepest point? Well, isn't the steepest point about where 7 is? So, and it's a positive slope. So I have no idea what the slope is. I'm just going to go up here. That's the steepest point. So that's where, again, this is our slope graph. That's where the slope is the maximum. And then this is what the graph is going to look like. It's going to be kind of like this. Curve up like that and down. That's a little rough, but that's kind of what it looks like. Okay? And now let's go to between 8 and 10. Do you guys agree it's getting steeper and steeper and steeper? Negative, right? Isn't this a negative slope here? So it's getting steeper and steeper, steeper, negative. And so it's going to look like this. Okay, and again, this is kind of a little guess what that is. I mean, it could be more of a straight line here. But remember, if I look at just the location here, that is not as steep as this because remember, this is the slope graph. So this spot right here is not as steep. This is a 0 slope here, and this is even steeper. So you can see it kind of goes, if I look at the original graph right here, it's kind of steep here, kind of steep, gets steeper, steeper, steeper. When it hits 10, it's actually, it's not. I mean, it could be, who knows what the steepness is, but it's definitely not steeper. That's why this corresponds to this on the slope graph. Okay? All right, let's take a look at, I made a bunch of other graphs for you guys because, again, I just want to practice with you guys on making derivative graphs. Okay, so you should have this handout as well. So let's kind of do a little investigation here. I'm going to draw my graphs over here. I'm going to do it in red so that I can easily point out some of the different features on the F graph. Okay, so remember, x units are x units, so everything corresponds with the x units, so we're going to put 2 tick marks going that way. All right, and then do you guys agree at this point here, right, isn't the slope 0? So let's plot 0 here. And what's going on here, it's a steep positive slope, and it gets less and less and less steep. But this is a positive slope here, and what is this? This is a negative slope here. Okay, so this is what that graph is going to look like. It's a little tricky, but it's going to look like this. It's linear. Okay, and again, I'm not looking for exact, I'm looking for you guys understanding kind of what it looks like. But what's going on is, at this point up here, that's saying it's a steep positive slope. Because remember, math fans, really important, when you go above, this is a positive slope. And when you go below, it's a negative slope on your slope graph. All right. So, like for this guy right here, it's a positive slope, but it's really steep over here, and it goes less steep, less steep, less steep, less steep, less steep. Here it is. It's steep here, and it goes less steep, less steep, less steep, less steep until you get to 0. And then it's not very steep at all because you're right here at this point, and then it starts going negative, and it gets steeper and steeper and steeper. So that's what your graph looks like. All right, let's look at the next one. Again, we're looking at our slopes here. And do you guys agree if I would just kind of look at the slope and I would draw a tangent line to that? Do you guys agree that's a negative slope? Okay, it's really a steep negative slope, and what happens as I get closer? Not as steep, not as steep, not as steep, and then it really turns into a 0 slope, and then what happens? It starts to be more negative again. So this actually is always negative, but math fans, at this point right here, isn't it a 0 slope? Okay, so let's get rid of kind of some of the stuff so we can see what's going on here. Okay, so let's graph this thing then. It's always a negative slope, but it's steep on the top left-hand corner, so this graph is going to look roughly like this. Okay, again, here's your point that I plotted. That's a 0 slope right there at the origin, and then it gets steeper and steeper and steeper. Okay, this is actually getting steeper, more like a y equals, and like an x cubed, right? It's getting really, really, really steep fast. All right, let's look at the next one. Okay, let's make a quick sketch here. Okay, we got a couple of points. Once again, when I look at the graph, the slope here is 0, slope here is 0, and the slope here is 0. Okay, so let's plot those points. If I would draw another tick mark on here just to make, well, I guess this is really the tick mark here, and that's in between. So it's like saying -1.5. So let's do that, and +1.5. So it's 0 here, it's 0 here at the origin, and it's 0 at 1.5. That's where the slope is 0. Now we got to look where it's the steepest. Do you guys agree it's really steep when you first start, that graph first starts out here? So let's clear this out here and clear that out. Okay. Do you guys agree right here it's a pretty steep negative slope? Okay, because again, if you're not sure, draw it in there. Oh yeah, it's negative. It's a negative slope. So it's pretty steep. That means I'm going to be somewhere over here. And again, I don't really know what my y value is. I mean, the slope could be -20, -50, -1.2 billion. I don't really know. So I'm just going to kind of get an estimate what it looks like. Okay, and where else is it steep? Do you guys agree it's steep probably at right here, the steepest point at 1? So that means that's going to be, and it's positive slope here. So I'm going to put a point up high where it's positive for slope. And then I'm going to look again at the right-hand side. So isn't that steep here, and isn't that a negative slope? So it kind of goes down here at 1. And then what happens at at this point right here? It starts to go. It's back up. Estimates. So this is roughly what that graph looks like. Okay, and let me erase all the stuff here so you can kind of see what the graph looks like. But that graph, again, looking at the slopes, right? Plot your 0 points, plot your minimum and maximum points. It helps you create a good slope graph. Okay, let's take a look at the next one. Again, I don't really have any x values, so let's just kind of draw something out here and just a couple y values here. All right, and a couple things. What it looks like is, first of all, this is a positive slope here. So if I follow along here, math fans, positive slope, and what is this right here? It's a zero slope. So we are going to plot a zero slope. Well, that's about -1. And there's also a zero slope right here, the positive one. So again, those are our points we're going to plot. But we notice this is that first red line I drew. Isn't that a positive slope? Okay, it's steeper over here, isn't it? It's steeper over there. So this is going to look like it's positive, so it's going to look like this, right? Because that's positive there. And then what happens when it hits that point? Doesn't it go negative a little bit? Just a little bit. And then, oh, I forgot to plot that one. Isn't that a zero slope also? Sure is. But it goes negative just a little bit, not a lot. So watch this. It's negative a little bit, and then it comes back to a positive slope for just a little bit. So positive slope just for a little bit, comes back to 0, and then starts to go a negative slope, and it gets steeper and steeper and steeper. So like that. And that's your graph. Okay? Not too bad. Okay, let's look at this last one here. This is an easy one. This is a piece of cake, man, because the reason it's a piece of cake is because these are constant slopes here. So I'm going to go up to 1, 2, -1, -2, and actually we need to go down to -3 here. And then I'm going to go out to -2 this way, and 1, 2, 3 out this way. Okay, so at from -2, x equals -2 to -1, isn't the slope up 2 over 1? So slope is 2 from -2 to -1. Okay, so -2 to -1, the slope is 2. And then when we go down 1 over 1, down 1 over 1. So slope is -1. And notice I have open circles because of the graph is changing, and that means the slope is not the same. The one-side limits are not the same, right? So really, and again, we'll talk about this tomorrow, you really can't take the derivative at those points, can you? Okay, because you don't know it. You're looking at the left side or the right side. It's continuous, but the slopes of the tangent lines are not the same on either side. All right, anyway, so we have -1 to 0, and then from 1 to 0, the slope is 1. And then the slope from, right, we're at this point right here now. So there's that slope 0 from 1 to 2. The slope is 0. Okay, and then from 2 to 3, it's down 1, 2, 3 over 1. Down 3 over 1. So the slope there is -3. That means I go down here at -3. Okay, and that's your graph. It's basically just a big old step function, not really in order, okay, but that's what it looks like. So that's just a couple more examples here, math fans, of doing all these different problems, all the different derivatives, and being able to graph it, and looking at data. So kind of had a little bit of a hodgepodge of stuff here, but hopefully you guys learned something. All right, have a nice day, math fans. Adios. Goodbye.